Welcome to our presentation of CAMDL, our system for cross-modal data discovery over structured and unstructured data lakes by Mohammed Al-Tabaq, Mayaresh Kanjar, Ahmed Al-Magharmeed, and Mohammed Shamir Ahmed. We begin by defining the problem. So first, let's understand what data lakes are. Organizations push large amounts of data into these things we call data lakes. Now, this data may be of a variety of formats, such as structured tables, semi-structured files, or unstructured text documents. Now, converting and parsing these documents into a homogeneous format is very difficult and very computationally expensive. But these data lakes still provide some value to organizations. And the main value is that you can get a lot of knowledge and a lot of insights from this large volume of data. The problem is the data discovery itself in these large data lakes becomes very challenging. Now, what we mean by data discovery is two things. First is discovering relationships among the data pieces, or what we would refer to as entities themselves. And the second is finding the relevant data pieces or entities to a user's given exploration task or query. Now, this is an example we'll go over about what a data discovery pipeline might look like. So we begin with the user that starts with a query. And the query in this case are the keywords thymidylate synthase. Now, the first type of discovery task is Q1, which is retrieving relevant documents to this query or this enzyme in this case. Now, we retrieve the relevant documents and we move to Q2. Now, Q2 is we want to find related tables to the keywords and sentences mentioned in this document. So in this case, the table on the right has the same keyword mentioned as those in the document. The other data discovery task could be Q3, which is you want to find tables related to terms highlighted in the documents that are not the original query term themselves. So in this case, pemetrexed is a term that is in the document on the left side and is also occurring in the table on the right side. Q4 is how do we expand the tables we have discovered by finding other joinable tables. In this case, these two tables join based on the drug ID. And Q5 is given these numbers, the vast number of tables we discover, how do we find more uniable tables to expand this search even further? Now, what this process shows is that the discovery tasks are usually iterative in nature. It is not the case that you submit a query and you get all the results in one shot. You want to go into further levels of depth, iterating upon the results that are retrieved in each previous step. The second thing is you want to switch between different modalities, which means you don't just want to stick to finding relevant text documents or relevant tables. You also want to find the relevant tables to the retrieved text documents. And the third is that for each of these discovery tasks from Q1 to Q5, you may want to use different features to optimize the results. Now, current SOTA solutions focus on discovery tasks that either are only within one data modality, mostly structured tabular data, or they might destroy the structural properties while performing transformations to these various data types to make them more aligned and homogeneous. The third thing is that they might inherit scalability problems because, again, these transformations applied to such a large volume of data might be costly. And the fourth thing is these solutions might be customized only to specific discovery tasks, such as entity matching, or to specific domains of data. Now, what we propose at CAMDL is a holistic data discovery system. In this pipeline, we treat both structured tabular data and unstructured text documents as first-class citizens, which means we try to process them in a manner that keeps their inherent structural properties intact. And then we want to support complex and heterogeneous and iterative discovery tasks within one discovery pipeline, which means using CAMDL, you can perform all types of discovery tasks such as Q1, Q2, Q3, Q4, and Q5 mentioned before. The one we'll be focusing on in this presentation is finding relevant tables to text documents or vice versa. So in this case, Q2 and Q3. Now, our architecture is as follows. We begin with the pre-processing phase. So we take text documents and we apply standard NLP transformations to them, such as tokenization, stop word removal, stemming. And then we end up with this bag of words that represent that text document. Now, this will be one unit of discovery, which refers to the text documents. The second pre-processing is done to the tables. Now, in this case, we treat each column as an entity. And these columns are tagged based on some heuristics that will determine which discovery task they will participate in. Now, from that, we extract from both these units of discovery, we extract features. Now, these features can be of various types. So some that we want to go over is syntactic similarity, which is basically the Jaccard similarity for overlapping terms. This can be approximated using mini-wise hashing, and then we store that in a locality-sensitive hash ensemble index. The second type is semantic similarity, in which case you take the embeddings of the keywords, you aggregate them, and then we store them in the ANOI index. And the third type is keyword similarity, which is another form of similarity that uses the BM25 similarity metric, and we use Elasticsearch for this index. And there are others which can be used, and we'll go over how this is extensible as well. Now, what these indexes allow is that finding pairs of similar text documents and tables, or the table unit of discovery and the text unit of discovery, in a not computationally expensive way. And then we want to create a novel joint representation for both documents and tabular columns in a new joint shared embedding space. Now, this embedding space should take into account all the similarity measures we mentioned before. However, training a model to create these joint embeddings requires a training data set, which we don't have, which is where the indexes we mentioned previously come into play. Now, before going over that part, we must understand what Snorkel is. So Snorkel is a framework which uses weak supervision to create probabilistic labels. So you start off with 2 input data, and you have a series of weak labeling functions. Now, each of these labeling functions on its own may be noisy or imprecise or just not that very good. In our case, the labeling functions would be the indices we mentioned. Now, each of these labeling functions generates a label, and then those labels are given to a generative model, which sort of reweighs them and combines them into one label. Now, those labels are then given to a discriminative model, which generates a probabilistic distribution over all the classes. In our case, we basically give the documents to different indices, the semantic one, the syntactic one, the keyword-based one, and others. And we get back hits for relevant columns. Now, that acts as a label, whether a column was retrieved in the probe of a particular index. Now, those labels, either 0 or 1, are given to the generative model, which is then given to the discriminative model, which gives us finally an output of a probability of matching between a document and column. Now, this gives us an approximated idea of what relatedness might be between this pair. Now, what this does is we leverage the state-of-the-art framework for label generation, which is Snorkel. We exploit all the available similarity measures from the profiler, which means that because we exploit all of them, it is robust to noisy and imprecise functions. This is also very extensible. So any other sort of individual way of determining similarity between documents and columns can just be added to this framework as another labeling function. This is very scalable as well, because you don't need to get this information or sort of index all the documents and all the tables. You just need a subset of them, because our objective is to create a training data set that can train the joint representation model. And this is tunable as well, given specific data sets or domains or tasks you may want to turn on or turn off particular labeling functions. Now, after this step, what happens is we want to basically create or train a model that creates a joint embedding for both tables and, for both columns and text documents. So we start off with our training data set generated by Snorkel, and we generate mini batches, which is just a random subset of documents and tables. And we choose a threshold for the probability. And anything above that threshold is considered a positive match, meaning this document and this column are similar. Anything below that is said that they're not a match. So in this case, the green ones represent a match, and the red ones represent this document and column pair do not match. We then train a deep learning model using the triplet loss function to essentially take an anchor point, and we basically mean pool over all the embeddings for the positive matches and aggregate over all the embeddings for the negative matches. And we want the model to learn using the loss function to make the embedding of that document closer to the embedding of the columns that it is positively matching to and further away from the ones that it is negatively matching to. And so at the end, you would end up with an embedding for that document that's closer to the embeddings of the positive documents and further away from the embeddings of a negative document. And this would be the same size vectors in a joint space. Now, for our data, we try this approach and we compare it to different baselines for 3 data sets. Here, what you see is for each of the data sets, we have some structured data in the form of CSV files or SQL files, and we have text documents as well. Now, for our experiments, we do 4 tasks: document table discovery. We also experiment on table joinability, table uniability as well. But mostly we're focusing on the documented table discovery here. Now, what our results show is that CMDL performs better than the individual benchmarks or individual labeling functions that we used in the Snorkel framework. So CMDL solo embeddings and CMDL joint embeddings and gold tuning, the blue diamond dot here basically is when you have a small manually labeled data set which you can use to improve the Snorkel labeling at the end. Now, what we see is it outperforms the other baselines in terms of precision and recall for all 3 data sets. And to conclude, basically, we introduce CAMDL as a holistic data discovery system for both structured and unstructured data sets. By this new novel joint embedding representation for both these modalities, what ends up happening is that you don't have to compute all the expensive labels which are in the indices for all the documents. You just need to do it for a small subset of the documents, train the model, and then just take the embeddings for each of the units of discovery after. And this is significantly cheaper and computationally less expensive than other approaches. Now, the weakly supervised model also allows for the generation of a labeled data set for a variety of tasks. And this is good because it's very extensible. You can add any labeling function of your choice to this and to improve the output or the performance of the model. And this basically promises consistent performance for various discovery tasks, as we mentioned, Q1, Q2, Q3, Q4, and Q5, but particularly Q2 and Q3, which is discovery across different modalities, across different benchmarks, and across different data sets. So that is our system. Thank you very much for listening.